In today's note, we are going to stick with the theme of probability, but look at theoretical probability. So the first thing we want to do is just kind of go through, just express each fraction in lowest terms. Again, just get comfortable with fractions as probability deals heavily with that. So if we want to express 3/12 as a fraction in lowest terms, we want to be able to, or we want to divide both the numerator and the denominator by the greatest common factor, or the greatest number that goes into both. So if I look at both these numbers, the number that can be divided into both, the greatest number is 3. So divide both the numerator and the denominator by 3, I get 1/4. 8/52, I want to do the same thing. The greatest number that goes into both is 4. So if I divide both by 4, I get 2/13, and I can see that I can't reduce 2/13 any further. Lastly, 20/52, the number that goes into both, the greatest number is 4, so I'm going to divide both numerator and denominator by 4 and get 5/13. So because we're looking at theoretical probability first, or now instead of experimental, there is a slight difference. And it's not so much in the math, it's more in understanding what we're looking at. And theoretical probability is a measure of the likelihood of an event happening based on all possible outcomes. So it may sound exactly the same as experimental, but the difference is experimental is what actually happened. Right? It's based on the experiment, it's based on us actually doing the events. Theoretical is what should happen. So based on what the probable outcomes are, what should happen. So theoretical is what should happen, experimental is what actually happens. The math is the same, except we just term it a little bit, or we word it a little bit differently. So a theoretical probability formula is the probability of an event is equal to the number of successful outcomes divided by the total number of outcomes. So it's very similar to experimental, but again, we're looking at what should happen, not what did happen. We are going to look at a deck of playing cards. So a lot of the probability questions that we're going to deal with, or theoretical ones, are based on cards. So if you're not familiar with a deck of cards, a standard deck has 52 cards, and there are 13 cards in each suit. The suits are spades, diamonds, hearts, and clubs, and the cards range from ace, or 1, to 13, or basically ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then jack, queen, king. Jack, queen, and king are termed face cards, right, because they have the faces on them, they have the actual characters, and just as a reference, there are different colors. The hearts and the diamonds are red, and the spades and the clubs are black. So again, just a helpful term, just a helpful reminder if you're not familiar with a deck of cards. So, example number 2, a card is randomly selected from a standard deck of cards. Determine the theoretical probability of each event. So again, here we're basing it on what should happen based on our numbers. Because we haven't done any event yet, or haven't done any trial, so it's not experimental. So drawing a club, so the probability of drawing a club is equal to the number of successful outcomes. So in this case, what are the total number of clubs that I could draw from? Well, in this case, I have 13 total clubs, because there are 13 of each suit, divided by 52, or the total number of outcomes, because there are 52 cards. And this I can reduce to 1/4, which makes sense because a quarter of the entire deck is clubs. What is the probability of drawing a queen, or the theoretical probability? So the theoretical probability of drawing a queen is equal to, well, we know the total number of outcomes is 52. And how many successful outcomes are there? So again, a success is considered drawing a queen. So how many queens are there in a deck? There's 1 per suit. So there are 4 total. And if I want to reduce this, I can reduce it to 1/13. Drawing a black face card. So the probability of a black face card. Again, I know the total number of outcomes from the deck is going to be 52 because there are 52 cards in a deck. Now, how many black face cards are there? Well, if I go back up and look, there are 2 suits that are black, the spades and the clubs, and there are 3 face cards per each suit, so there's 6 in total. So 6 over 52 is my theoretical probability, and I can reduce this to 3 over 26. D, not drawing a diamond. So the probability of not drawing a diamond. So in this case, again, I still don't know the total number. It's going to be 52. Now, how many successful outcomes are there? Or basically, how many cards are not diamonds? Well, there are 3 suits that are not diamonds, and there are 13 in each suit. So you could do 3 times 13, when you get 39. So 39 cards are not diamonds, so we have successful outcome of 39 successful outcomes. We can reduce this to 3 over 4, which makes sense because there are 3 suits out of 4 that are not diamonds. Example 3, we're looking at a bag of marbles. So a bag of marbles has 12 red marbles, 8 black marbles, and 4 blue marbles. If you randomly pull out one marble, determine the probability of, and then we have multiple examples. So in order to help us, we want to know, 1, what is the total number of marbles, right? Because those are the total number of outcomes. So the total is 24. If I add them all up, I have 24 marbles in the bag. So I have 24 outcomes, or different outcomes. So for the first one, the probability of red, I know the total is going to be 24 because there are 24 outcomes or marbles in total. And how many red marbles do I have? Because red would be considered successful. In this case, I have 12 red marbles. Oops. So 12 over 24, and I can reduce that to 1/2. So, or 50%. Right, so again, remember, we can always change it to a decimal or a percent. So you could say 50% chance of getting a red marble. For B, I want to know grabbing a red or a blue marble. So if I want to grab a red or a blue marble, again, I know my probability or the total number of outcomes is 24. Now I need to look at how many successful outcomes do I have. In this case, a success is considered red or blue, which in this case is 12 red and 4 blue. So that gives me 16 possible outcomes that are considered a success. And then when I reduce it, I can reduce it to 2 over 3. For C is the probability of not grabbing a black marble or not black. And in this case, again, we could do 2 things. Here again, I can look at, I know for my fraction it's going to be out of 24. I can look at all the successful outcomes. In this case, or a successful outcome is not black, so how many marbles do I have that are not black? And then in that case, it's just my red and my blue marbles, which is 16, which I can reduce to 2 over 3. Or I could see that in example B, grabbing a red or a blue marble is considered the same thing as not grabbing a black marble. So just different ways of wording kind of the same thing. Example 4, we're going to go back to drawing a card from a deck, but we're going to look at a a new situation. So here in example A, we are drawing a spade or a jack from a deck of cards, and we want to know what is the probability of that happening. So if I look at the probability of a spade or jack, I know my total number of outcomes is going to be 52 because there are 52 cards in a deck. Now, the next thing is, how many successful outcomes are there? And here's where we have to kind of think a little bit differently. So, thinking of spades, there are 13 spades in a deck, and there are 4 jacks. So you may think, okay, well, there's 17 options right there, so it's going to be 17 out of 52, or 17 over 52. But what you have to consider is that 1 jack is also a spade. So because there's 1 jack that is also a spade, it cannot be counted twice. So because when you look at spades and jacks together, you do have some overlap. And you can't overlap it because then you would be counting a card twice, which would make your probability not true. So, therefore, you have 13 spades plus 4 jacks, but you have to subtract the overlap, so you have to minus 1 jack of spades, which will give you 16 total possible outcomes. So in this case, I have 16 out of 52, which is equal 4 over 13, which we can reduce to 0.31 as a decimal, or 31%. So again, you have to think of what you're looking for, and if there is an overlap in what the items are, then you can't count, you have to remove that overlap. For the next example, for B, drawing a black card or a face card. So here we have to think of a couple things first. First, there are 26 black cards because 2 suits are black. So there are 2 times 13, which is 26. 2, there are 12 face cards in total. But the third thing we have to consider is that 6 face cards are black, and we cannot count them twice. So if I was to do just 26 plus 12, I would be overlapping or counting cards twice. So what this means then is that I need to do 26 black cards plus 12 face cards minus 6 black face cards, which will leave me with 32 total outcomes or possible outcomes. So that means for my probability, the probability of it being black or face is going to be 32 outcomes over 52, which is equal to 8 over 13. So that is my probability or theoretical probability of drawing a black or face card from a standard deck. So again, this is looking at theoretical probability. While the math is primarily the same, just keeping in mind that theoretical looks at what should happen compared to experimental, which is what does happen or what did happen. And when you're dealing with certain situations, if you have successful outcomes that overlap in our example, we were looking at cards. If you have events or outcomes that overlap, you have to remove that overlap so that you don't count an outcome twice. So again, just be careful of what the question's asking. Make sure you read it carefully and actually think about what you're actually looking for.